All right, so we're going to do one last example here on related rates. This final example, if you remember back when we were doing optimization, I had said this. Sometimes when we're working with Pythagorean or with triangles, we use the Pythagorean theorem. This was the example I was thinking of. This one, we're going to draw some triangles, but the idea, the Pythagorean theorem isn't going to be necessary because although we're going to draw triangles, the diagonal, which is what the whole point of the Pythagorean theorem is, doesn't really have anything to do with the question that we're being asked. It's just sort of part of the picture, but we don't ever need to measure it. We don't ever need to figure out how it's changing. So example 7 says, a person who is 180 centimeters tall is walking at a rate of 2.4 meters per second towards a 3-meter tall lamppost. We need everything in the same units. So this is 2.4 meters. This is 3 meters. How many meters is 180 centimeters? 1.8, yeah. Cool. So we'll just call that 1.8 meters and get that out of the way right at the beginning. The lamp casts a shadow behind him, and the shadow gets shorter as he gets closer to the lamppost. So we'll draw our picture here. This is a really common setup. So a lot of the setups that we do are really common for these types of problems. So we have two things. We have a person and a lamppost, and the person is walking towards the lamppost. So here's our person walking towards the lamppost, which is right here. That's totally what a lamppost looks like, right? A sun on a stick. And his shadow gets shorter as he gets closer, so we actually have to draw a shadow on this person. So I was thinking of a slightly different picture until I actually thought about it. Let's move him a little bit. We missed it. Move him a little bit to the right so we can get a shadow. There we go. Boom. Leave myself absolutely no room to work. And then here's where we get the triangle. The idea here is the shadow comes from the tip of the light, and then all of the light coming down from the lamppost is blocked by his body, and that's where we get our triangles from. So let's think about our numbers here. We'll label them, and we'll decide if they are static or dynamic. The person is 1.8 meters tall. Is that changing? No. So that's static. Yeah, right, I know. There's a spot where if you really want to argue it, well, I mean, it's changing, but not over the amount of time we're talking about. And what's the other part? The lamppost is 3 meters tall, and that obviously is also not changing. Okay. He is walking at a rate of 2.4 meters per second towards the lamppost. So he is going this way, 2.4 meters per second. So the idea with a problem like this, and this kind of matches some of the things we talked about yesterday. I just realized I have a fatter pen on because I was using my drawing pad yesterday. That's why everything's so clunky. When you're moving 2.4 meters per second, that also means that the length between you and whatever you're going towards or away from is changing by 2.4 meters per second. So the distance between him and the light pole is changing by 2.4 meters per second. Is the distance between him and the light pole getting bigger or smaller? Smaller, yeah. So that distance is decreasing by 2.4 meters per second. So something moving causes a distance to change at that rate. So the ladder example, and if you think back to that one, I didn't say this yesterday, but that was the idea with the ladder example. The ladder was moving, it was falling down, but that meant that the distance from the ground to the ladder was decreasing by whatever that rate was. So something moving causes a distance to change. So we should label that distance, and I'm going to label that distance x, which makes dx dt equal to that rate.
Please excuse the interruption. At this time, all students taking the literature keystone, please report to your testing room. And just a reminder that no cell phones are allowed, so please put your cell phones in your locker. And that stairwell 1 and stairwell 2 will be closed during testing.
Alrighty. And then the question we're answering here in letter A is when he is 2 meters from the lamppost, how fast is the length of his shadow decreasing? So that x value is 2, but is that x value static or dynamic? Is it changing or is it not changing? It's changing because he's getting closer to the lamppost. Yeah. So you can kind of see there that when we label our picture, we label the static variables with their numbers, and we label the dynamic variables with x's and y's and things like that. What do we need to figure out? Yeah, the length of the shadow, right? Or not so much the length of the shadow, but its rate, right? But yeah, so we need to label the length of the shadow, so we can label the length of the shadow y. And our goal here is to figure out dy dt. All right. Do we know any of the diagonal distances? No. Do we want to know any of the diagonal distances? Do we want to know any of the diagonal distances? No, we don't want to know them. Do we care about how fast the diagonal distances are changing? The diagonal distance. No. That diagonal it's part of the problem. It's what causes us to be able to do with what we're doing here. But we never need it, so this problem is going to be done completely without the Pythagorean theorem. What we're going to do here is we're actually going to use similar triangles. When you have light, whether it's the sun, whether it's the lamppost, the two triangles in your picture are similar triangles. And our two triangles are the triangle made by the person, his shadow, and that diagonal that we don't care about, and the lamppost, its distance to the end of the shadow, and the diagonal that we don't care about. One of the properties of the way that light works is that those two triangles will be similar. Okay? So if they're similar, that means we can make a proportion out of their sides. So if I take a look at the person, I can do 1.8 to y and write that as a ratio. So my formula or my equation here that I'm going to use is 1.8 over y. And that equals the same two sides of the green triangle, which would be 3 over what? Did you say xy? Would I multiply those to find the full distance? X plus y. Yep, you got it. Now, you don't want to differentiate that as is, because you'd end up with a lot of, not necessarily quotient rule, but you would still have negative variables and stuff like that. Cross multiply first. Get 3y equals 1.8x plus 1.8y, or 1.8 times the quantity x plus y. Hopefully you can, I think it's just easier to have it that way. And I could differentiate there, but as a matter of fact, I'm just going to, collect all my y's on one side and make my life a little bit easier. Subtract 1.8, that should give me 1.2y equals 1.8x. And from there, it's just a matter of taking the derivative, which is super easy. Remember, we're taking with respect to t, so every time we work with the variable, it has to get chained with that variable dt. So the derivative of 1.2y is 1.2 dy dt, yeah, equals 1.8 dx dt, yeah, boom. From here we can plug in. And one of the things that always throws people on questions like that, our only two variables that we need to plug in for are dy dt and dx dt. Did we need the two? No. It turns out that it doesn't matter where you are in this problem. It doesn't matter if you're 2 meters from the light post pole, it doesn't matter if you're 10 meters from the light pole, you'll get the same result. This relationship is like a steady relationship. It doesn't depend on how far you are from the light pole. So we get 1.2 times negative 2.4 equals 1.8 dx dt. Yep, you're right. I was thinking it was inconvenient that the 1.2 and the 2.4 were being multiplied instead of divided. I even looked up too. So it's 1.2 dy dt, which is what we need. And that equals 1.8 times 2.4. I'm going to avoid rushing to my calculator because I think all of this is mental math if I just forget about the decimal points for a minute. And that's negative, right? Yep. So I'm going to divide both sides by 1.2, which I'll actually show. I usually don't, but I'm going to show it because 2.4 divided by 1.2 is just 2. Yeah, so this cancels to negative 2, which means that my dy dt is negative 3.6. And it's a change in a length. So our change in our length over here was meters per second. This is also meters per second. I think one way to think about these, we got a little bit of a bigger number here. As the person is walking towards the light post, both x and y are going towards 0, right? If you're standing directly under the light post, you're not casting any shadow. I mean, within reason, there might be just you can't get right directly under the light post, but those things are both going towards 0. So x has to shrink to 0, and then y, which is bigger, has to shrink. I guess, do we know that y is bigger? I was just sort of thinking, which would be bigger? Would x be bigger or would y be bigger? I don't know. I thought that made more sense until I started talking it through. That's all right. But yeah, that's the answer we got, negative 3.6 meters per second. I was thinking of this length, not this length when I started talking, so ignore what I said. And that length's what we need to think about next, because letter B is asking how fast is the tip of his shadow moving. And again, if you're trying to figure out how fast something is moving, you're talking about how fast a length is changing. And that's, kind of the connection that you need to make. This tip is moving at a rate at which this whole length, I guess say this the right way, this tip is moving at the rate at which x plus y is decreasing. So as he walks, this whole shadow is moving with him, and the tip is moving. The tip represents the length of x plus y, so it's moving at the rate that x plus y is decreasing. This would be trickier to figure out if you were really just thinking about his shadow, because as he walks to the light post, both endpoints are moving, right? So we just consider the length x plus y because as he walks to the light post, this is stationary over here, and his shadow is the only thing that's moving. And the way we do that is by using x plus y. So we actually need to figure out what d dt of x plus y is. There are a couple different ways to do this. I think the best way to do it is just replacing it with a variable, because we actually end up with a much simpler situation. We're going to call z our x plus y. We're going to get basically our same formula from before, but we're going to replace x plus y with z. So we get 1.8 over y equals 3 over z. Which gives us 1.8z equals 3y. Which, again, when you're working with these are the easiest things in the world to differentiate. We'll just do 1.8 dz dt equals 3 dy dt. Plugging in, we have dy dt from our previous problem, so negative 3.6 meters per second. That's our dy dt. Again, the math's going to work out nice on this one. So we get 1.8 dz dt equals negative 3 times negative 3.6. Again, I'll write it out with my division. Dz dt equals 3 times negative 3.6 over 1.8. And 3.6 over 1.8 simplifies to, I heard it, negative 2, yep. So dz dt equals negative 2 meters per second. It would be negative 6 because I never multiplied by 3. I was about to say that doesn't make sense because it needs to get faster. Yep, negative 6. And this was what I was trying to say earlier. I just was thinking about the wrong thing. Both quantities, all three quantities need to go to 0 as you approach the lamppost, right? Because you're not going to cast a shadow if you're directly under the lamppost. So the idea is, if you want this to go to 0 in the same amount of time that this smaller quantity goes to 0, then this has to be shrinking faster. And that's why we got a bigger rate, negative 6, versus either negative 3.6 or negative 2.4. As a matter of fact, looking at, so we did the problem that way. Look at our three answers. What is, if I just, look at what I had here. I had d dt of x plus y. Can I sort of distribute that operator and do dx dt plus dy dt? Would dx dt plus dy dt give us what we got for dz dt? Yeah, absolutely. So we actually could have done that. I think somebody in BC asked me that when I went over this. Can we distribute, but this is an operator, so don't think that this is a variable, but it does work because that's how differentiation works. You can differentiate across a sum, so we could have done it that way as well. All right. Okay, so the rest of the time we have to work. The problems start off relatively simple. These are just practicing the math component of it. No word problem whatsoever. You need to, when you're doing these, differentiate everything with respect to t. So when you see something like y equals 3x to the fourth plus 6x in problem number 1, you're going to do dy dt when you take the derivative of y equals 12x cubed dx dt plus 6 dx dt. Everything is going to get chain ruled with a d, whatever your variable is, dt. Okay, so this one kind of almost just looks like something where you're just going to put like y prime, not what you do there. It's dy dt on that one. But once you've done that for all 4 of these problems, it's really just a matter of then plugging in what you know and solving for what you don't know. Looking at number 4, the formula they gave us is a equals 1/2 bh. It is a triangle, yep. When I go to take that derivative, what do I need to use? No. I'm taking a derivative. I don't ever take the Pythagorean theorem when I use the derivative. I do have to use the ADT, that is correct, but it's 1/2 BH. Where's the composite function? You gotta say it louder. Product rule, right? 1/2 base times, that's a product, height. So you will have to use the product rule here. So you're going to have derivative of the first, which will be dB dt, times the second. So you're going to have this plus a this. Remember, your first is 1/2 b, so every time you're working with your first, there's going to have to be a 1/2 there. Cool. From there, you'll start hitting a series of word problems. Actually, wait, sorry. So I want to explain this page too before you hit the word problems. This is strictly a matching problem. You're not solving anything in any of these problems. These are just sentences you might see inside of a word problem, and your job is to pick which one of these says the same thing as this. Okay, so this page shouldn't take very long at all because you're not solving anything. You're saying which one of these 4 choices matches the sentence that's being given. Then you'll hit the word problems. The first few sort of match stuff that we did yesterday. Maybe that number 15 changes. When you get to 16, I believe this one somewhere in it is going to bring an angle into it. Maybe we'll either go over, if you get there early, I'll kind of go over it with you, but this is going to involve trig. So when you get to that theta, we'll throw some trig in the mix. At some point, we'll probably do that problem as a group, but if you get there early. Yeah, the 16 and 17 both have an angle in them. Yep. Right. Look at Dan go. He's on 3 already. Half hour to get lots done. Love it. All right, Italian blend. 1, 2, 3.